Hi, this is Suneet Kumar and welcome to the demo lecture on circular motion. So today we are going to learn about circular motion and the banking of roads. So first of all, let us understand what is banking of road and why is it needed. So banking of road is when when you have a road and when you elevate the outer portion of the road above as compared to the inner portion of the road. So this is called banking of road, and we need it because you cannot rely on friction completely to give the necessary centripetal force. So in the previous lecture and in the previous classes we have done where we saw that friction is needed to provide the necessary centripetal force when a body is moving in a circular motion. So when a body is moving in a circular motion, when a body is moving in a circular motion, what happens? Its natural tendency is to go straight tangentially. Okay. So now, for that, in general, what will happen? That the body for that body to move in a circular motion, there should always be a force which should pull it towards inside, radially inwards along the center of this circular motion. So generally, this force is called centripetal force, and this is provided by friction. But you cannot rely on friction, as we saw in earlier classes that when there is a rainy season, what happens that because of rain, the friction reduces between the tires and the road, and there is a tendency that the vehicle will slip away, will skid away, right? And there may be an accident occurring. So to avoid such kind of situation, the architect who designs the road, they generally do the banking of roads. So what is banking of road? Let's go forward and see that. So what is important here to understand is friction is not a reliable source for providing the required centripetal force to the vehicles. So you can see, the vehicle, when it goes in a circular motion, the tendency is always to go outward, and there may be skidding happening. So as you can see in this, video, and the vehicle may go outwards, and then it can get, overturned or something. So, because we cannot rely on friction, the safer course of action would be to raise the outer edge of the curved road above the inner edge. So as you can see here, in generally when we go to hill stations, you would have seen it, that the outer edge of the road is elevated as compared to inner edge of the road. So this phenomena is called banking of roads. Now, how does it help? Even when there is less friction, how does it help the vehicle to maneuver this curved path is what we are going to learn here. So, as you can see, you would have seen these tracks being built. So whenever you see a racing track, you will see that the outer edge is always elevated as compared to the inner edge, and that is what is banking. So, let us calculate the maximum safe velocity of vehicle on a banked road without friction. So when you go on these, hill stations, you would have seen that, there is this speed limit which is mentioned. For example, the speed limit is, 40 km per hour. So that 40 km per hour is a safe speed. So let us calculate the safe speed, safe velocity of vehicle when there is no friction. We assume that there is no friction. If there is friction, it will definitely assist, and our speeds can go higher than the maximum saved limit. But when we assume that there is no friction, what will happen? How does centripetal force come into action is what we are going to see here. So you can see the diagram here. So here, this is the road surface, and the force which are acting on this vehicle is weight mg, which is downward, and the normal reaction would be perpendicular to the surface. So if this is the surface, right, and this is the car, so you will have weight mg downwards, and let's say the angle of elevation, if it is theta, then and this is the normal reaction N, it will have two components. This normal reaction will have two components, one horizontal component and one vertical component. So if this is theta, we know that this angle will also be theta, and this is 90 minus theta, and similarly this is theta, right? Now the component which is perpendicular, vertical, that will be equal to n cos theta. We have seen, the component which is along the angle theta is always the cos component, and the component which is horizontal is equal to n sin theta. Now this n sin theta component provides the necessary centripetal force. So let us write the equation. N sin theta is going to provide the centripetal force, which will be equal to mv square over r, where r is the radius of the circular path, and your n cos theta will be equal to mg, right? Now, this n sin theta has to be greater than equal to mv square by r. So we are writing equal to because we are finding the maximum velocity which is possible. Now so let's say this is this equation first and this is this equation 2. When you divide these two equations, what you are going to get is sin theta over cos theta. So n and n will get cancelled. So we can write this n sin theta over n cos theta is equal to, or we'll use this inequality sign so that there is no confusion. So n sin theta had to be greater and equal to mv square by r. Now this will be greater and equal to mv square over r divided by mg. M gets cancelled, so and n gets cancelled. So you will have tan theta greater and equal to v square over rg. Now when you take rg on the other side, we will have v square is less than equal to rg tan theta, or v is less than equal to root under rg tan theta. Okay, so this is the maximum velocity which is possible even when there is no friction. Because of banking, there will be a centripetal force, and the body, the car will be able to move in that circular path, and the maximum speed with which it can go is root under rg tan theta. So if we do not consider friction and then we have mentioned the maximum velocity at some place, then the cars, the drivers will see that maximum velocity and will try to drive within that velocity range and avoid any such accidents. Now let's come and see, let's go ahead and see that when there is friction also, then what will happen. Okay, so I'll just remove this. I hope you have seen this and you have understood it. Now see here. Now in this condition, in this case, we are also considering friction. So first of all, we'll decide in which direction the friction is going to be. So let's say this is your, again, curved path and this is your vehicle, right? Now there is a weight downward which is mg. Now the tendency of this will be to skid outwards. So the tendency is to go outward, friction will be inwards. So friction is in this direction. You have a normal reaction N which will have two components. We saw this n cos theta in this direction and n sin theta in this direction. The friction force, now because this angle is theta and this was also theta, friction will also have two components. So you will have F sin theta in this direction and you will have F cos theta in this direction. Now these two forces together is going to provide the necessary centripetal force, and mg and F sin theta together is going to be balanced by n cos theta for vertical equilibrium. So for vertical equilibrium, when you write this equation, you will write n cos theta is equal to mg plus F sin theta. Also, friction force, we know that it is equal to mu into n. So friction force F is equal to mu into n. Now replace this here. So this is your first equation, this is your second equation, and this force F cos theta plus of n sin theta is equal to mv square by r. So this horizontal force provides the necessary centripetal force, and so these are the three equations. Now what we are going to do, we are going to replace this friction force in both these second and third equation. So what will you get is n cos theta is equal to mg plus mu n sin theta, and the second one is mu n cos theta plus n sin theta is equal to mv square by r, right? So let's say this is your fourth equation and this is your fifth equation. Now what we are going to do is, see, you have this mu n sin theta, you can take it on the left side, and again you will have two equations. So when we take it to the left side, you will have n cos theta minus of mu n sin theta is equal to mg, right? Now we divide this is, let's say, equation 6. So we divide equation 5 by equation 6. What we are going to get is v square over rg. So v square over rg, this is equal to, you can take n common in these equations. So when you take n common, you will have mu cos theta plus of sin theta divided by, you have n taken common, you will have cos theta minus of mu sin theta, right? Now when you cancel this n, so your v square is going to be rg, and then you divide by cos theta in both numerator and denominator. So what you are going to get is mu plus tan theta by 1 minus mu tan theta. And if you have to find v, so this will be square root of rg into mu plus tan theta divided by 1 minus mu tan theta. So when friction is also available, you will always see that this is greater than rg tan theta, because you are adding mu to it. Root under rg tan theta, it is more than this maximum velocity here. When you are considering the friction as well, it will be greater than the previous case where we were not considering the friction. So here we can see that when friction is also available, then the speed limit goes higher. So the speed limit, if we have mentioned, considering that there is no friction, the vehicle can move even at a greater speed. So we would have seen that, it is written 20 km per hour, and then still our driver is driving at, let's say, 40 km per hour, and we are still able to move in that circular motion. But that is only because we are using the friction available there as well. But if we don't consider friction, we should drive at a speed which is being mentioned there. So students, I hope this concept is clear to you. So you can have a look at this. So we'll stop the lecture here for the day, and thanks for joining in. Hope you have liked the lecture and you have understood the concept. Thank you and bye.